All right, so how are we going to deal with force now and Newton's laws? So in the previous video, we defined rotational inertia. And so we said, okay, so instead of mass, when we're looking at rotational motion, we're going to use rotational inertia. And so if we looked at acceleration, we have something that we call an angular acceleration. So we have almost all of the ingredients for Newton's second law, but what would be the analogy for force? Okay, so as you can see, it's going to be what we call the torque. And just like for rotational inertia, it will contain information about the force, but it's going to be a little bit more complex. So just like rotational inertia, we used mass, but we had to look at the way that the mass was distributed. Here we're going to look at the force, but we're going to need to look at how it's applied, so where, and the direction. Okay, so I want you to think about what happens when you open a door. So the door starts a rotation, and so I could take a piece of paper to represent my door. All right, so this could be the hinges, and then we could have it open and close. Okay, so if you look at where the handle is going to be, it tends to be pretty far from the hinges, so on the other side. And so there's a really good reason for that. If you actually go to a door right now and actually try to push it close to the hinges, you'll see that it's going to be a lot harder to have it open. Okay, so that's one thing. So that means that it's going to be a lot more efficient to push further away from the hinges. Okay. Another thing is, okay, I could push far, so I would be far over here. But if I push this way, it's going to be pretty good. If I push like this, it's not going to do anything. All right. So if I push off from the side, it's not going to open my door at all. So the direction in which the force is going to act is going to be very important also. So the torque is going to depend on three factors. One is going to be how much force you're actually producing. So how much force are you applying to the door? Okay. The second one is in which direction are you pushing, or in which direction is the force acting? And then finally, where are you pushing? So what is the point at which the force is applied? So those are three things that we're going to have to consider when we define the torque. So torque, by definition, how do we calculate it? It's going to be what we call the lever arm multiplied by the force. Okay, so the force is how much, so this is in newtons, and that's how much you're pushing. But then the lever arm is going to include, so this is going to include the information on the force. And this here is going to be defined by the lever arm. So the lever arm is going to depend on where the force is applied and the direction in which it's applied. So we have some examples over here, and you can see that we have an object that can rotate around this point over here. And we have 4 different scenarios. We are pushing here fairly far from this axis of rotation here with a fairly strong force. So in this case, the force is we push perpendicular to the surface. So our level arm is going to be this distance here between where the force is applied to the axis of rotation. So over here, same idea, but you can see that we're not going to have as strong of a torque, and that's because the force is smaller. Okay. Now we could use the same force, all right? So you can see that this is the same strength. We're pushing with the same amount of force, but we reduced the value of the lever arm. So in this case, so again, the lever arm would be here, that is not going to give us as strong of a torque. Okay. And finally, we can push at an angle. That makes the lever arm different. So what's going to be important is the distance from that's perpendicular to the force. So in this case, and I would not worry too much about this because this is a more complex case, this is going to be our lever arm. And you can see that even though we're pushing with a fairly large amount of force, we have reduced the lever arm by a lot by changing the angle. And that means that our torque is not going to be as large, and we're not going to be able to produce as much. So here, what are we producing as we're pushing? We are pushing with a force that's giving us a torque. And from what we learned from Newton's second law, that's going to result in an acceleration, but not any acceleration is going to result in an angular acceleration. So if we reduce the torque applied to the object, we're going to reduce the amount of angular acceleration. So this is our Newton's second law, but for rotational motion. And so you can see that we are going to use, so here this would be the equivalent of F equals ma, but we replace, so torque by, force by torque, mass by rotational inertia, and linear acceleration by angular acceleration. But same idea, you would apply it in the same way that we did in the chapter on Newton's laws. Okay. So again, just you can take everything that we've done before, and once you draw these analogies, you can see that you just have to replace the symbols with the correct ones. Most of these, you may have noticed a trend at this point. When we go to rotational motion, those angular variables are usually a Greek letter. So A becomes alpha, all right, for example. All right, so this was torque and how we can use that in Newton's second law now to figure out an angular acceleration, the same way we would have found the linear acceleration of an object if we were able to find the net force applied on that object. Again, net means that we have to account for all of the torques of all of the forces that are acting on our object and produce and are going to produce a torque. Really quick before we close off here, I just want to point out that if you had gone all the way and pushed with a force like this, all right, then the lever arm would have reduced to 0. And so in that case, our torque would have been equal to 0, which means that you would not produce any angular acceleration at all, which you can try it at home. Open that door, push from that axis towards the hinges, but from the side, and you'll see that it's not going to rotate at all. Okay, so it's really cool that in this concept and definition of torque, we can carry so much information about the rotation. So again, if you want to be as efficient as possible, that means that you're pushing as far from the axis of rotation as possible, and you want to push perpendicular to the object over here. And one thing that we haven't really talked about is how the mass of our object is going to affect the result, but that is essentially contained in this information right here. So just be careful and make sure you use rotational inertia and not mass in that case. All right, so now we have all the ingredients. You also go back and look at energy, and we'll do that in the next video. Thank you. Bye.